Assalamu alaikum students. I hope you are all doing well and welcome to my new video about game theory. And remember, in the previous video we were talking about dynamic games, and we understand, or we did some illustrations of game theory, and we talked about the Stackelberg model of duopoly. So the plan for today is that I will move on to the next type of game, which is called static games with incomplete information. Okay, and we will try to understand some of the basic elements in these games, and I will give you an example, and I will also show you how to find Bayesian Nash equilibrium. So if you remember, we can divide game theory into two main branches. One is the static game, and then we have dynamic game. Okay, and you remember that in static games the players have to move simultaneously, whereas in dynamic games the players have to move one after the other. And then we further divide static games on the basis of information. So if we have static game with complete information, or if we have static game with incomplete information. Okay, and similarly we can further divide our dynamic games into dynamic games with complete information and dynamic games with incomplete information. So if you remember, the difference between complete information is that we know everything about the game, like we know what are the pair function of the other player, and incomplete information means that we are missing some information about the other player's functions, pair functions. So if we have a static game with complete information, we use the idea of Nash equilibrium. And if we have the dynamic game with complete information, we have the idea of subgame, perfect Nash equilibrium. So today we are going to start static games with incomplete information, static game with incomplete information. And in this type of games, we need another equilibrium concept, because Nash equilibrium will not work, subgame perfect Nash equilibrium not work, so we have to come up with a new concept which is called Bayesian Nash equilibrium. Bayesian Nash equilibrium. And our final topic in this course will be dynamic games with incomplete information. So in that game we will have another equilibrium concept, because these three will not work there, so we call it perfect Bayesian Nash equilibrium. Okay, so this is the structure of the game theory, and now we are going to talk about the dynamic static game with incomplete information. Okay, so let us now talk about some of the basic elements of a game. Basic element of a game, and it depends if we have the complete information okay, or if we have incomplete information. Okay, and we are talking about static games. Okay, so if we have a static games with complete information, and remember this is where we started our game theory course, and what are the basic elements there? The first element is that we need to know who are the players. Okay, so this is the first element. And then the second element is what are the actions available for each player. And then the third element was what are the payoff when the game ends. And in case of incomplete information, again, the first element is that we would like to know who are the players. Okay, but now we do not know some information about the other players. So that is why we further need to know what are the types, what types of player we are facing. Types of player, and then also we need to know what are the beliefs, common beliefs. I will explain these things in detail, but just for comparison I'm showing you what are the basic elements. And then the second element will be actions, and the third element will be payoff. So now you see that the main difference between the complete information game and incomplete information is that in incomplete information we have to further divide our player element into two things, like that is we know how many types of player we are facing, because we do not know the exact, we do not have all the information about the other players. So that is why we need to know what are the types of player we are facing, and then what common beliefs we have about those types of player. And I will give you examples, don't worry about that. And then we have actions and payoffs. So let me start these static games with incomplete information by just defining the equilibrium concept. And we start by the definition of Nash equilibrium. So if you remember the definition of Nash equilibrium, is that a Nash equilibrium is a set of strategies one for each player. Okay, so Nash equilibrium is a set of strategy, and we have strategy for each player such that no player has incentive to change his or her strategy given what the other players are doing. Okay, so this is the definition. A Nash equilibrium is a set of strategies, one for each player, such that no player has incentive to change his or her strategy given what other players are doing. Okay, what other players are doing. So now I'm going to write the definition of Bayesian Nash equilibrium. Okay, so we have Bayesian Nash equilibrium. So now I'm going to modify this equilibrium concept. So you'll see it will be very similar definition. So what is a Bayesian Nash equilibrium? So I'm just saying that a Bayesian Nash equilibrium is a set of strategies, one for each type of player. Such that no player type has incentive to change his or her strategy given the belief about the types what the other types of player are doing. Okay, so now you see I just modify the definition of Nash equilibrium to write the definition of Bayesian Nash equilibrium. So you see here the only difference is that we are adding type of player. Okay, we are adding type of player and the belief. So these are the two differences in the definition. So otherwise it is the same concept. So what is the definition of Bayesian Nash equilibrium? A Bayesian Nash equilibrium is a set of strategy, one for each type of player, because we do not know the type. We do not have some information about the other player. So we say a Bayesian Nash equilibrium is a set of strategies, one for each type of player, such that no player or no player type has incentive to change his or her strategy given the belief about the types and what the other each type is doing. Okay? So maybe some of the wording is not 100% correct, but and also I apologize for my writing. It's not very good writing, and it is difficult to write on the computer. But anyhow, I hope you got the idea what is the difference between Nash equilibrium and Bayesian Nash equilibrium. Okay, so this is the definition of Nash equilibrium in good handwriting, and this is the definition of Bayesian Nash equilibrium in Bayesian Nash equilibrium, and then you can see that the only difference is the types and beliefs. Okay. Okay, so let us now try to understand these Bayesian games with the help of an example. So we are taking an example of two players game. Okay, and we have player 1 and we have player 2. Okay, but player 1 has two types. Okay, type A and type B, and player 2 has only one type. So there is like some uncertainty here, some incomplete information. Player 1, of course, he knows if he is type A or if he is type B, but player 2 does not know if he is playing a game with type A, player 1, or player 2 is playing with type B, player 1. Okay, so this is incomplete information that player 1 has two types type A and type B, and player 2 does not know if he is playing a game with type A or if he is playing a game with type B. So this is the basic setup. So here we have player 1. Okay, player 1 is here, and then we have player 2 to here. So we now have the pair of matrices, and if the type of player 1 is A, then we are looking at this game. If the type of the player is A, then we are looking at this game here. So let me tell you, this is the game if the type of the player 1 is A. On the other hand, if the type of the player 1 is B, okay, if the type of player 1 is B, then we are in this game. Okay, so this is the basic setting, and we now have to find the Bayesian Nash equilibrium of this game. And let me tell you a few more things about this game. So we know that player 1 is here and player 2 is here. So player 1 knows about player 2's payoff, but player 2 does not know if he is playing with type A player 1 or type B player 1. But he has some beliefs. Okay, so now I am going to explain the word belief. Belief means what is my expectation or what is my knowledge about about each type of player. So my knowledge as a player 2 is that the probability is P for type A player 1, and the probability for type B player 1 is 1 minus P. So this is my belief. This is my knowledge that there is a probability distribution over the types of player 1. So with probability P, the type of the player 1 is A, and with probability 1 minus P, the type of the player 1 is B. So this is called common belief. And then in each game, each type of player 1, the payoff matrix is different. So it means that player 2 does not know if he is in this game or if he is in this game. Okay, so there is uncertainty or there is incomplete information for player number 2 about player number 1. Okay, so let us now try to solve this game, and we start with player number 2. So, and now we first look at the situation where player 2 is playing a game with type 1, type A player 1, which means that we are in this game. Okay, we are in this game. So if you look at player 2, we see that for him left is giving 4, and it is better than right. Okay, if player 1 is playing up, and then if player 1 is playing down, then again left is better than right. So it means for player 2 who is playing with type 1 player 1, for him left is better than right, always better. So it means there is a dominant strategy. So left is a dominant strategy and right is dominated by left. Okay, so this is if player 2 is playing with type 1 player 1. So now we look at if player 2 is playing with player 1 but with type B player 1. Okay, and now we can again analyze this payoff matrix, and we can see that now right is better than left if player 1 is playing up, and again right is better than left if player 1 is playing down. So again we find that that there is a dominant strategy for player number 2, but now right is dominant and left is dominated by right. So it means right is better than left. So it means there is no consensus. In the previous, if he is playing with type A, we find that left is dominant, but if he is playing with type B, then right is dominant compared to left. So there is no consensus. We cannot find any dominant for player 2, which is dominant for both types of player 1. So now let us move to the player 1 analysis. If we look at player 1 and if he is of type 1, then we can see that the down is better than up, and also it is better here. So it means down is always better than up. So it means if the player 1 is type A, then he will always choose down. So his best response is down of type A. So it means player 1 will always choose down compared to up if he is of type A. So now we look at the other possibility that player 2 is now B type, and we are looking at the payoff of player number, sorry, this is player number 1 and this is player number 2. So now we are comparing the payoff for player number 1 if he is type B. So now you see that the 6 is better than 5 and 0 is better than -1. So what do we see here? We see that up is a dominant strategy, and it is down is dominated by up for player number 1. So he will always choose this strategy. So up is better than down in case player 1 is of type B. Okay, so this is the dominant strategy. So let us now summarize what we have done until now for this game. We say that for player 1, type A, down is better than up. So he will play down. Okay. And then we also find that for player 1 type B, okay, up is better than down. Okay, so he will play up. Okay, so we have solved the game for player 1 for both type A and type B. What about player 2? Player 2 is confused because he do not know if he is playing with type A or if he is playing with type B of player 1. So we still have to find the best strategy for player number 2. For player number 1 we already decided, but for player 2 we have to still solve this game. So let us now again discuss the game for player number 2. For player number 1, we already decided that as a type A, he will play down, and type B will choose up. So we already have the solution for player 1 of each type. But if you look at the game or payoff for player number 2, if he plays left, if player number 2 plays left, how much he can get? He can get 3, he can get this 3, or he can get 2. Because, why I'm saying this? Because player 2 is not sure if he is going to get this number or if he is going to get this number. Okay, so this is the incomplete information. So, but we know that with probability P, he will get 3, and with probability 1 minus p, he will get 2. So let us now calculate his expected payoff, because he's not sure if he's going to get 3 or 2. So we can calculate the expected payoff. So now this is expected payoff. Expected payoff. So he will get 3 with probability p, and he get 2 with probability 1 minus p. So this is his expected payoff if he plays left. And if he plays right, so he can get 0, okay, or he can get 4. Again, there is an uncertainty because player 2 does not know if he is playing with type A or if he is playing with type B. But he will get, 0 with probability P, and he will get 4 with probability 1 minus P. So we can calculate expected payoff. Okay, we can find expected payoff. So what are the expected payoff for right? So he will get 0 with probability P, and he will get 4 with probability 1 minus P. So for player number 2, his decision to play left or right actually depends what is the value of p. Okay, so the value of p will determine if this is bigger than this, or if left is better than right, or if right is better than left. Okay, but we can always find a value of p. Let's suppose we say that left is the utility of left, or pay of the left, is greater than right. Okay, so which means that 3p plus 2 into 1 minus p has to be greater than 0p plus 4 into 1 minus p. So this has to be true if we say that left is better than right. So we can solve this. So we say 3p plus 2 minus 2p is greater than 4 minus 4p. So if we rearrange it, we get 3p minus 2p plus 4p is greater than 4 minus 2. Okay, so if we solve this, okay, so how many p's we have here? So 3, 1p, and 4p, 5p, and this is 2. So we have 5p is bigger than 2. So p will be bigger than 2 by 5. So now we can say that if p is bigger than 2 by 5, then left is better than right. So now we have a strategy for player number 2 depending upon the value of p. So if p is bigger than 2 by 5, left is better than right. If p is less than 2 by 5, then right will be better than left. So we have a strategy, equilibrium strategy for player number 2. Okay, so now we have solved the Bayesian Nash equilibrium, because we have solved the game for each player and each type of player. So if we look at player 1 of type A, we said that he will play down. Okay, so this is the best response or best strategy. And player 1 of type B will choose up, because that is best for him in that situation. But for player 2, the decision depends upon the value of p. So if p is bigger than 2.5, he will choose left. Okay, if p is less than 2.5, 2 by 5, he will choose right. And finally, if p is equal to 2.5, then he can mix between left and right. So that will be a mixed equilibrium. Okay? So this is called Bayesian Nash equilibrium. Okay, so in this video I showed you, or I introduced you, the static games with incomplete information, and then I also explained you how to find Bayesian Nash equilibrium. But this method of finding Bayesian Nash equilibrium was a bit difficult, like you have to think about many possibilities. But in the next video, I will show you how to find Bayesian Nash equilibrium in an easy way. And thank you very much for listening, and see you in the next video.